Chapter 14 is about light and sound in the atmosphere. Our driving question: what is responsible for the various optical phenomena observed in the atmosphere, and how does sound propagate through the atmosphere? The chapter opens with a case in point about an optical illusion, if you want to call it that, called Fata Morgana. And Fata Morgana is the appearance of what looks like a castle in the distance that's kind of lifting up out of the ground or out of a sea, if you can imagine that. It happens on the horizon after sunrise, after a really clear night where radiational cooling has been happening all night long, and there's low-level inversion. And you get multiple distortions kind of stacked on top of each other, kind of a shimmering thing going on. So it's a mirage, and as we'll learn a little bit later in this chapter, it's caused by refraction of light waves that travel through the atmosphere that's stratified into layers of different densities. So atmospheric optics all have to do with the sun's rays traveling through the atmosphere. And as we've learned, when the sun's rays enter the atmosphere, they're either scattered or reflected, or in our case, what we're looking at in this chapter, refracted. So we'll talk about refraction in just a moment, but refraction happens by cloud droplets, ice crystals, or raindrops. Visible light, as you'll recall, is one portion of the electromagnetic spectrum, and it happens to be the portion that our eyes are designed to see. So you're going to hear a lot about refracting light in this chapter, and refracting light is simply like what you see here with a prism, where light rays are coming in at some angle and they meet something, in this case a prism, but as we'll see in atmospheric optics, it's usually an ice crystal or a water droplet, and the different medium, whatever it is, water, ice, or liquid, it causes the light to change direction. So it refracts it, it bends it. And here, because this is a prism, you're seeing the breakout of the different colors of the visible light spectrum. And this can happen in the atmosphere also. So let's talk about some different phenomena, beginning with what's called a halo. There's a picture of the halo there. This is kind of a super duper halo because it's double. You see two halos here. A halo is a whitish or sometimes slightly colored ring of light that surrounds the sun or the moon. And it forms because there's tiny little ice crystals that make up really high thin clouds, like really high cirrus clouds, that refract the sun's light. So there's little ice crystals in there, and as the sunlight is going through the ice crystals, it bends or refracts, and it scatters it or redirects it in such a way that you see this halo around the sun. So here's a diagram that shows refraction in water, and it's the same thing in the atmosphere. It's just maybe a little easier to grasp with water. So if the sun's rays are coming in at 90 degrees, like you see in this picture in the top right, there is no refraction. But if the sun's coming in at an angle, like we see in this top left picture, then it's going to refract when it hits the water. So we would kind of expect it to continue along a straight path, but in fact it refracts as it hits the water. And what it does is it causes these optical illusions. So here's a picture of a guy in a boat, and he's looking down into the water. He sees a fish, and he sees the fish as being over here because the same thing is happening. The light that his eyes are seeing is being refracted. So here's the actual fish. He's seeing light reflecting off of that fish, and when the light crosses from the water to the air, it refracts and plays this little game with his eyes. So here's refraction as it plays with the atmosphere for a halo, like we just saw the picture. So we have an ice crystal, in this case a hexagonal ice crystal, and the sun's rays are coming down, and the ice crystal causes the sun's rays to refract, and when we see it, when we see that light, we're seeing this refraction effect, and so it causes this halo to form like you see here. The angle of that halo is 22 degrees, which is the angle that we're seeing the light diffracted relative to if the, relative to if the light were shining straight down. So the angle of refraction is 22 degrees. There's also another type of refraction for halos that can happen with an ice crystal that is more tubular, rectangular, and it's lying flat like you see here. It's the same principle. The sunlight's coming in, it meets this ice crystal, and it bends the light. But this time it bends it at a greater angle, 46 degrees. So we're going to see excuse me, a slightly different kind of halo. Another phenomenon is a sundog, and you see the picture here with the satellite receiver. There's you see the picture here with the receiver dish, where we have these two bright lights of kind of rainbow lights on either side. These are called sundogs, and they're bright colored spots that are on either side of the sun. So the sun in this picture is kind of behind this antenna, but you can still see that the sun is there. So these occur when the sunlight is refracted by crystals, again, plate-like crystals, that are falling through the atmosphere. So we've got very high clouds again. You can see in this picture, high clouds are always made up of ice crystals, and when the crystals are just the right type, you might see a sundog. A sun pillar, like you see in the bottom picture here, is a pillar of light, a shaft of light that appears above or below the setting or rising sun, and it's also caused by the reflection of light off of horizontal ice crystals. A rainbow is something that we all definitely have experience with, the arc of concentric colored bands. So a rainbow's a little more sophisticated. There's a little more going on. So here it's a raindrop, it's not an ice crystal. And what happens is the sunlight's coming down in the direction that you see indicated here. It encounters a raindrop, so this is like a gigantic raindrop that's been blown up so we can see what's happening. And as the light meets that water surface, it refracts, and then it reflects off the backside of this raindrop, and it refracts again as it leaves the raindrop and enters your eye. So there's a refraction, a reflection, and then another refraction going on with these raindrops. So you see here the angle is 42 degrees, which means that the recipe for seeing a rainbow is, number one, there has to be raindrops in the sky. Number two, the sun has to be shining, so the sky cannot be completely clouded over. You have to have sunlight. And the sun has to be behind you, no higher than 42 degrees above the horizon. So if the sun were higher in the sky, then the rainbow would be down below the horizon. Our eyes would not see it. Here's a picture of a rainbow, a double rainbow. So you see how the light gets broken down into its individual color components. The violet is always closest to the sun. It gets refracted first or broken out first. It's the shorter wave. And then we go through the spectrum. We go through blue, green, yellow, orange, and then red is always on the outside. And then if you see a double rainbow, it is just the opposite. It goes from red out to violet. And sometimes you might see a triple rainbow, in which case it flips again, so it goes back from violet to red. So here's a little more about a rainbow. So here we see our observer looking out. The sun is behind him. There's raindrops in front of him. Here's the line of sight to the sun. So the sun's rays are coming in. They hit these raindrops. They do the refraction, reflection, refraction thing. And then by the time that light reaches his eyes, it's he's seeing the arco iris, as it's called in Spanish, the rainbow. And the thing actually would make a full circle. It's just that we don't see it. It's always sitting on the horizon. So I've never seen the pot of gold. I suppose it's there somewhere, but technically there's a whole circle there. So there's nowhere for that pot to be. Here is a picture of a double rainbow. When you see what's going on with a double rainbow, same kind of thing. The sunlight's coming in, it meets the raindrop and refracts, and then it reflects off of the backside, reflects again, so it's reflecting twice here, and then refracts again to get to your eyes. So here you would have double refraction, or double reflection rather, within the raindrop, which causes the double rainbow. There's also something called a fog bow, which forms just like a rainbow does, except in fog instead of water droplets. So basically fog is a cloud at ground level, and a cloud is made up of lots of little cloud droplets, which are similar to raindrops, except for, there's a bunch of them and it's down on the surface, and we've got that kind of white color of the cloud anyway, like we do not have when we're seeing raindrops. We just see the rain in front of a sky. But with fog bow, we're seeing a cloud, or the fog anyway, and then the bow, but you don't see it broken out into colors. It's just white because there's so much going on here with the cloud or the fog itself. Too many wavelengths of light interfering with one another, so we just see it as white. A corona is another type of optical phenomenon in the atmosphere. This is a series of alternating light and dark concentric rings that may surround the moon or the sun. It's less common around the sun. Usually you see it around the moon. So we see this a lot. If you look at the moon in Arizona, go out at night, sometimes when there's a little bit of cloud in the sky, you'll see a big ring around the moon. And if you look closely, you'll see there's a bright ring and a dark ring, and maybe it alternates even more. This is caused by diffraction of lights around water droplets that make a thin veil of clouds up in the sky around the moon. We've talked about diffraction, and what can happen here is we can have constructive interference or destructive interference, and this is just where you have light waves that have been diffracted, and if you get the crests of these light waves coinciding with crests of another light wave, then it intensifies the white part. This is what makes the bright white part. And the same thing, if the crest of one wave coincides with the troughs of another wave, then they kind of cancel each other out, which creates the dark band. Here's a picture of a corona of the sun. It can happen when you have these high cirrus clouds. So you can see kind of a bright circle around the sun, and then here's a big dark spot. This is not the best picture. I've seen much better examples of corona around the moon in Arizona, and maybe you have too, or if you haven't, it's a good opportunity to go out and look at the full moon each month and see if you can identify a corona. A glory is a bright little ball of rainbow light that you see shining down on a cloud below you. So you have to be up above the clouds to see a glory. And this can happen when you're in an airplane flying up above the low cloud layer, or maybe if you climb a really high mountain and you break through the clouds and it's sunny up on top, or however you can get up above those clouds. And what happens, it's basically like a rainbow, but you're just seeing it in the clouds. So you see the picture here, there's concentric rings of color around the shadow. So this would be the plane's shadow right inside there. And it just refracts and reflects the light just like we saw with the rainbow. So same thing going on here. The light comes in and it gets reflected off the back and refracted as it's coming in and going out. And it produces a glory down on the underlying clouds. And again, it's interesting to remember that each person is seeing their own individual optical phenomenon here. So if you were up on a mountaintop looking down at a cloud layer with somebody else sitting right beside you, and you see both of your shadows on the cloud, but you only see the glory around yourself. Your partner is having the same exact experience. They're only seeing the glory around their self, because it all has to do with the observer. It's happening within your eye. A mirage. This is like the Fata Morgana that the chapter opened with. This is an image of a distant object that appears displaced, and it's caused by light being refracted in the atmosphere because of different densities of air. So if you have like a temperature inversion, or it doesn't even have to be an inversion, just where you have different densities of air kind of sitting on top of each other, then that's enough to cause the light to play these games with your eyes to make you kind of see things that aren't there. So with a mirage, there's something called a superior image. This is when light rays are reflected from the distant object. They bend more sharply than usual, that causes the object to appear higher up than normal. And an inferior image, or mirage, is when the rays are reflected less than normal, so the object appears lower than normally. So mirages can sometimes be displacements of something that's real, or not really something that's unreal, like in this case, in this desert mirage, where somebody might think that this is water, like a lake in the distance. It's actually the sky, and it's just being refracted and playing kind of this game with our eyes because of the different densities of air. So sunrise and sunset is a time of mirage. And what happens here is we see the sunrise or set, whichever one, and we think, that that's exactly where the sun is. Maybe the sun's distorted like you see it here, which is kind of a mirage effect. But the fact that we're seeing the sun at all is a bit of a mirage. So in this image here on the left, here's my observer. And the actual location of the sun here is just on the horizon. So you can see when he looks out, if he were actually looking at the real sun, it would be just setting. But because of this mirage effect, his eyes and the light from the sun bends. So the apparent image of where the sun is, he's going to see the sun as being much higher in the sky, like not even setting yet, getting ready to set. So we are still seeing the sun looking like it's up in the sky or setting in the sky even after it's gone down. So it makes it a little complicated. There's a bit in the book that you can read about where on the equinoxes, where we're supposed to have 12 hours of daylight for all locations on Earth, they measure day length by the time that the sun crosses down below the horizon for sunset and the time it crosses above the horizon when it clears the horizon at sunrise. So when you use that kind of measure, it's not taken into effect the fact that this mirage effect is happening with locations. This effect is a little bit different for different places on the Earth. It's more extreme when you get towards the poles, and less so when you get towards the equator. So we call that period twilight, the period of light that follows sunsets or comes before sunrise, where the sky is illuminated but the sun is below the horizon. It's caused by scattering of sunlight, and the length varies with latitude and time of the year. So if you've been to the tropics, you may have noticed that there's not really much sunrise or sunset. There's not a lot of fanfare. You don't get this long, drawn-out, beautiful colors thing. It's just, bam, there's the sun in the morning, and then, bam, it goes down at night. And there's not really much twilight. Whereas when you move poleward, you have long periods of twilight. At the extreme of the poles, you can have kind of twilight for many months without the sun really ever rising above the horizon. So twilight comes in 3 stages. There's something called civil twilight, and then nautical twilight, and astronomical twilight, and they are measured by where the sun is below the horizon. So you can see the values here. For civil twilight, the center of the sun's disk is 6 degrees below the horizon. For nautical twilight, it's 12 degrees below the horizon, and for astronomical twilight, it is 18 degrees below the horizon. So at twilight, you may see something called crepuscular rays. These occur at the beginning of evening twilight, and like the picture here, they appear as beams of sunlight that are radiating from the sun. And you kind of draw these pictures when you're a kid, you know, with the sun casting out its rays. And it happens because of scattering in the atmosphere and the extreme amount of atmosphere that the sun's rays have to pass through when it's low on the horizon, like it is at twilight times. Another phenomenon around twilight is something called the green flash. So this is a thin little green rim that appears briefly at the upper edge of the sun as it's setting. So you maybe will see this on a distant horizon with a very clear atmosphere, and it is a flash in the lower latitudes. So one of the places in the U.S. where this is supposedly easy to see, I never saw it there, is Key West. So it's just a flash. You watch the sunset, and if you get to see that green, great. If you go poleward, it lasts longer, so it's not just a flash. It can last for several minutes, up to half an hour. And it's a consequence of refraction and scattering of light when the sun is low on the horizon. So remember, the way scattering works is by the time the sun is low on the horizon like this, and the light reaches your eyes, all of the violets and blues have been scattered out, and we're left with these other colors. And if you go down the spectrum, it's violet, blue, and then green, right? And then yellow, orange, and red. So you get that little bit of green in there, but just for a moment at our latitudes. All right, a little bit about sound waves. Again, air, temperature, and density affect not just light in the atmosphere, but also sound. And wind also comes into play with the sound and how sound waves travel through the atmosphere. So sound waves travel faster in warm air than they do in cold air. So you can get variations seasonally as well as with distance, depending on what's happening in the atmosphere, if it's warmer in one area and cooler in another. So a change in temperature gradient with distance will alter the speed. It causes a refraction of sound waves. And normally what happens is sound waves refract upward, away from a warm surface. And refraction may produce acoustic shadows, which are areas where sound isn't heard. So you can read in the textbook about studies that have been done on the Civil War in the United States, how the sound of the cannon and the different sounds of the war could be heard in some places and not in others because of what was happening atmospherically. Thunder is probably the most common sound that we hear in the atmosphere. It's that sharp clap of rumbling after lightning discharge. So as we talked about, lightning causes kind of an explosion in the air, and because of that there's a shock wave that gets generated and it propagates outward. And we talked about in our thunderstorm section how light travels faster than sound, so we see the lightning before we hear the thunder. And if that storm that's generating the thunder and lightning is more than 12 miles away, you're probably not going to hear the thunder, but you'll see the lightning. It's called heat lightning. So nothing mysterious about it. It's kind of a misnomer, but you'll see lightning but not hear thunder. So we have this little formula that we can apply, if you have ever heard this one, where you count the seconds between when you see the flash of lightning and when you hear the thunder. And for each 5 seconds that you're able to count, that represents 1 mile of distance from where that lightning struck. So the closer the two are together in time, the quicker you want to run and seek shelter. You don't want to be outside when you're hearing thunder just as soon as the lightning's flashing. A couple other things in the atmosphere. Sonic booms happen with aircraft that travel faster than the speed of sound. So the pilot won't hear this, but when the plane goes faster than the speed of sound, it produces a sonic boom, which, just like thunder, propagates in all directions, and we can hear that. And also aeolian sounds, which is a general category of the sound that you hear when wind blows over certain things out there, like maybe power lines or towers of some sort, and you hear this kind of eerie sounding wind that blows. Those are just called aeolian sounds.